introduction part, what a solar flare is. So it's basically an intense burst of radiation which comes from the release of the magnetic field associated with an active region. So usually it is really intense and has an emission of electromagnetic radiation. So we have classified the solar flares based on their X-ray flux into categories, which is X, M, C, B, and A. X being the most intense one and having the most effect, and A being the least. And we have 4 phases of solar flares here, which is precursor, impulse, peak, and decay. Starting precursor, where the intensity is minimum and it starts there, and where the impulse, the particles start to accelerate, and next followed by peak, which where there will be maximum intensity, and then decay after that. And here we have a graph of a different class of solar flares. As you can see, that we have X category, and we have C categories based on their peaks. And next we'll get into what Solexis is. Solexis is basically solar low energy X-ray spectrometer, and it's designed to observe the X-ray emissions in the energy range of 2 to 22 kiloelectron-volt. And it has silicon drift detectors. We have 2 silicon drift detectors to analyze the data and track the solar flare evaluation. So we'll be getting into what are the technical parameters of this. We have energy range of 2 to 22 keV and energy resolution which is at 170 eV at 5.9 keV. And we have time cadence. Time cadence is nothing but the time interval which is 1 second. We're going to take data in each 1 second so that we can notice rapid changes, like the rapid flares. And we have detectors. We already discussed it, like STT1 and STT2, which will be more elaborated further into the discussion. So, and we have calibration source and number of channels in the spectrum. We have 340 channels in the spectrum, which have been channel width is 1 to 68 channel and 169 to 340 channel. And these are the key technical parameters of Solex, and I'll be passing on the mic to my teammate.
Good evening, everyone. Since my previous speaker has explained that what Solex is, so we'll discuss how we'll take the data and choosing an event. So for choosing an event, we are using GOES data, and we will look through a different flare event. And after that, we are here choosing the 12 September 2024 flare data. And it is since we have 5 types of flares like A, B, C, M, and X. So we consider a moderately intense flare M5, and we try to collect the data from the Solex as well from that data. So for downloading and extracting the Solex data, we just visited Pradhan website, and we have downloaded the Solex data, and from that Solex data we look into the intensity of the flare, and through which we want to know that we'll calculate we'll collect the data from SDD1 or not. Here SDD1 and SDD2 are silicon drifted detector, the 2 detector of Solex, which collects photon counts at the rate of 10 to the power 5 per count. And after we downloading the data, the Solex data, there are 3 types of Solex data: LC, GTI, and PI. We'll discuss the next slide about these data. And after downloading the data, we using Solex tools and Expect for extracting the light curve, and it's checking its thermal properties and spectrum. So data structure, as I have said in the earlier slide, there are 3 types of data. GTI file, it's good time interval GTI file. It gives time interval of valid data of a day, or you can say like, and then LC data stand for light curve file, and it keeps the photon counts in the energy range, which Solex, we are using Solex, so the energy range is 2 to 22 kiloelectron volt. Then PI file is pulse invariant spectral file, which data we can use for the recorded the pulse for the spectrum recorded, and for it gives the time interval per each pulse a day. So here we can see all the file is level 1 file. Since level 0, the 0 level is not implemented, so we are using level 1 data for fittings of like light curve, spectrum, and the other 10% temporal variance. So in the next, my fellow friends will like we are using those data for discussing these light curves and all. So my fellow friends will explain how the light curve vary time and everything. Thank you.
Hello. So, using the data from those previous files that my friend mentioned, we have tried to visualize the data. The above plot shows the counts on the y-axis and the time in units in the x-axis and counts on the y-axis. This plot is the date, the event which was chosen is 2024 9th, 2024 12th, 2024 September, and where we have also separated the good and bad time intervals. Bad time intervals are basically where your most of the data points are missing, means the photons have not been able to capture or detect. We have made the rough estimation for the classes of flares depending upon this graph. As you can see, this graph shows the classes of flare, but there are lot of small scale or solar flares are there which are hard to identify or hard to estimate their scale. So to minimize that, we have tried to smoothen the data by taking the moving window over 60 seconds and averaging out on those 60 data points on those 60 seconds, which basically minimizes the background noise. And here you can clearly see that the main structures or main flare signatures are being enhanced, and the background noise is being reduced, and we can observe the small class flares also. The next slides will be explained by my next fellow.
So, we're selecting a time interval. Basically, we have chose one of the prominent flares which were available for us in the last slide. So, we selected a time interval which is showing one of those prominent flares. From there, we have taken a interval which has the peak of the flare. That 60 seconds we are going to analyze now. In this 60 seconds, you can see that the flare has its almost peak value. Here we will be generating a spectrum, and the time we have taken was from 9 minutes 40 seconds to 10 minutes 40 seconds. That is the start time of your flare. I mean, the peak, where the peak starts to be prominent. And using this flare, if you analyze it properly, at one of the places we have some spectral breakdown. That is because the channel changed from 168 to 169. We have binning difference. Like from channel 1 to channel 168, we have one binning, and from channel 169 to 340, we have the other one. Due to this change, there is a small spectral breakdown at around 165 in the channel number. Like around that place, we'll be having a breakdown. And these counts were efficient from the 57th channel. Like all the other channels before 57 couldn't take the data properly. But in this particular flare, from 57th channel to 350th channel, we could take the data properly. I would hand over it to the next person.
So after visualizing the data, after choosing our point of interest in which point we want to do the analysis, we have choose the peak of the flare. So now, as we have gotten the spectra, what we will find from the spectra, we will try to model it using some pre-designed model database we have. So this is our spectra. So to fit, we have used a Chianti isothermal model to fit our spectra, and which is based on the thermal brainstorm data. And so for the Chianti isothermal model have these parameters in which so we have the first row tells about the temperature log T, which is like 6.39. The 18th is the argon abundances, calcium abundances, Fe, nickel, and the last column row shows the emission measure values. So what we did to identify, if you can see in the previous slide, we have some peaks. So to fit our model according to these peaks, what we will do, we will free these particular parameters, what I have shown, and make an initial guess for a temperature. Suppose in the initial guess, the temperature is given 6.3, the log P is 6.3. So we have made it because we know the flare is where the heating mechanism happens, so it will have a higher temperature. So we have taken log T as 7, which means 10 millikelvin temperature. So, and also we have free our parameters for the argon, calcium, Fe and nickel, so that when we are fitting it, we can make it to fit the best. We have the reduced chi-square. So using the chi-statistics, we perform the fitting and reduce the parameters. So the plot you are seeing is that the data points, black data points, is the actual data we have for our spectrum, for our particular event what we have chosen, and the blue curve shows the model we have fitted to this. So as you can see, this clearly fitted our data points what we have, and also have fitted the different emission line we have. So the first emission line, as you know, we have three parameters. First was the argon. We can see is a little emission peak was there, so we have fitted this. So the second one is the calcium. The third one is the iron complex, and the fourth one is the nickel peak. We have. So we have seen the data has been very well fitted. Also to check whether the data is fitted not by visualizing, also by the chi-square values, we have del chi upon the energy values. You see the data has been properly fitted, and we have a very good chi-square value, which is 1.67, which was 1.67. So after doing the fitting, we have these particular parameters. So as we know, we have the initial guess for temperature was 7, log T is 7. After fitting, we got a better temperature value, which is 7.17, and all the elements like argon, calcium, Fe, Ni, we got the abundances for them, and also we got the last row test for the emission measure for this particular spectra we have. So now Vinay will tell about the conclusion.
So in conclusion, in this project, we basically seen the mechanism of the solar flares, understand about the solar specification and their different data structure like light curves, PI file, and GTI files, and how we can choose the event and download the data from the website, and visualize the data using different packages like XSpec, and how to pin the data, selecting the time interval for doing the science objectives, and generating its spectra, and after that how can we fit this data with our models like isothermal plasma model, and finally deducing the parameters like temperature, emission measures, and element abundance during the flare events. Thank you.
Okay, I have to go back to the no, back to the next. So what is the terms of the so if you talk about the key, so what is the concept is
So the concept is as we go to the higher limits, let us count. That's why we
and from temperature seems
make sure of when the fail is happening, how many counts are there, how to bring, how to make this spectrum fitting more better.
And also you said also some spectral play at one of the channels, like around 80 meters. So how do you take care of it or not taking care of it?
So, you know, we have a channel for, we have two different channels. The initial one is 46, and another is 94. So, in the Solex, we have while we are doing the analysis, we have that which will decompensate for them and there is no break in it. Otherwise, we can also, as we know, there is a width is a difference in the width, so we can divide our data widths by 2 to give them the same overall distribution.
Okay, so you will connect it. And okay, if not, then we have final presentation from first